Hello everyone, this is example 6 on pipe friction in turbulent flow. The flow rate in a 300 millimeter diameter pipe is 225 liters per second. The flow is found to be turbulent and the center line velocity is 3.7 meters per second. The flowing fluid has a density of 900 kilograms per cubic meter. Determine the following: the friction factor, the head loss per kilometer length of pipe, the shear stress at the walls of the pipe, the shear stress at distance of 30 millimeters from the walls of the pipe, the velocity at the distance 30 mm from the walls of pipe, and the friction or shear velocity. So first, let's have the mean velocity because the center line velocity and the mean velocity are related in terms of F from the formula V sub C equals V quantity 1 plus 1.326 square root of F. So V is 4 times Q over pi diameter square. So the mean velocity of flow is 3.183 meters per second. Then this is the relationship between centerline velocity and mean velocity in terms of friction factor. So substitute 3.7 equals 3.183 quantity 1 plus 1.326 square root of F. So 3.7 over 3.183 minus 1. Then the answer divided by 1.326. Then the answer squared. So F is 0.01500. Then the head loss per kilometer length of pipe, because the pipe is circular, head loss is 0.0826, friction factor 0.015, length 1000, discharge 0.225 square over diameter 0.3 to the fifth. So the head loss in a distance of 1 kilometer or 1000 meters is 25.81 meters. The shear stress at the walls of the pipe, that's tau max, given by gamma head loss diameter over 4L, or F friction factor density velocity square over 8. Gamma head loss diameter over 4L, or friction factor density velocity square over 8. So using this formula, it is 0.9 times 9,810 newtons per cubic meter, head loss 25.81, diameter 0.3 divided by 4L, 4 times 1,000. 0.9 is 900 divided by 1,000, so 0.9, specific gravity of the liquid. So tau max is 17.09 pascals, or that's the shear stress at the walls of the pipe. If you use this formula, then we have 0.015 times 900, 3.183 square over 8. So it is 17, practically they're the same. It's because of the velocity and friction factor maybe, because we round off to 4 significant figures. But they are practically equal. Then the shear stress at the distance 30 mm from the walls of pipe, since RO is 150, 150 minus 30 is 120, so that means shear stress 120 mm from the center line of pipe. Since shear stress varies linearly from 0 to maximum at the walls of pipe, so shear stress at 120 as to 120 equals tau max 17.09 as to 150. The direct formula is gamma head loss R, which is 0.12 over 2L. That's the direct formula, but this is better because you don't need to memorize. So 13.67 pascals. Then 6.5, the velocity at the distance 30 mm from the walls of pipe, or that's the velocity 120 mm from the walls of pipe, from the center line. So we use V sub R equals V sub C minus 5.756 square root of tau max over density, log of quantity RO over RO minus R. So it was derived, and therefore in my lecture video, therefore you must watch how this formula was derived. And if you can also follow the derivation or you derive it by your own, then you can memorize that formula. the velocity profile, which is logarithmic for turbulent flow. So substitute V sub 120 equals 3.7 minus 5.756 square root of 17.09 over 900 log of 150 over 150 minus 120. So solving for velocity 3.146 meters per second. Then the friction factor or shear velocity. It is square root of tau max over rho, this one. Or velocity square root of F over 8. So V as sub asterisk is tau max over density, or mean velocity square root of F over 8. So it is equal to 17.09 over 900. So it is 0.1378 meters per second. If you check the other formula, it is 3.183 square root of 0.015 over 8. And the answer is the same, 0.1378 meters per second. So I provided you with two formulas so that at least you can remember, recall one of them rather.